Welcome back. This is part two of charge and charge transfer. Going to pick it up on this slide. So I'm going to go over three different ways that you can transfer charge around. These are the basic ways. So we're going to cover all three of these: charging by friction, charging by conduction, and charging by induction. All right, so let's start with friction. Friction is kind of the most straightforward one. Right? If you just pick items out of the universe, most atoms and objects are neutral, meaning they have equal number of electrons and protons. And so one of the sort of simplest ways to get some charge transfer happening, and this is what happens when you get like a static cling, or like you zap yourself on a doorknob or the handle of your car, is something became charged by friction, meaning literally one object scraped electrons off the other object. So in this picture you can see the neutral object on the left was losing an electron, and the one on the right now has that electron. So the one on the left is short an electron, so that means it has more protons than electrons now, so it's an overall positive charge. And the guy on the right who gained the electron now has an overall negative charge. So you've gone from a situation where you had two neutral objects to two oppositely charged objects, and that's always going to be true in the case of friction, right? Charge is actually a conserved quantity, and I mean truly conserved, like in the sense of energy, momentum, and angular momentum. Not like the fake charge, not the fake conservation law of conservation of mass that will be yanked away from you, that I yanked away from you this year. But charge is actually one of the fundamental six conserved quantities. So why does the electron go from one to the other is basically a chemistry question, right? It's related to this idea of electronegativity. Certain atoms hold on to their electrons more tightly than other atoms do based on their atomic structure. It's not quite exactly the same thing, because in chemistry class you're looking at one individual atom in isolation or one molecule in isolation, and here we're talking about a macroscopic sort of surface feature of a big object, and that might not quite track your electronegativity values from chemistry class, but it's the basic idea. How hard is that one substance holding on to its electrons, which is a function of how many protons there are and how close those electrons are to the nucleus and how loosely they're bound and all those kind of things. And it's the actual force of friction that provides the work done by friction as you scrape those two objects back and forth that gives you the energy to free that electron and transfer it over. So why don't you look this over and make a choice. Let's say after charging by friction, the two objects will always be, could it be any of these, or will they always be the same, or will they always be opposite? Okay, and the answer is they're always going to be opposite, right? Assuming you started with neutral objects, one guy's losing electrons and the other guy's gaining them. So the loser of electrons becomes positive and the gainer becomes negative. All right, so when you are zapped by a doorknob, which of these is the pair of oppositely charged by friction objects? Right, so specifically, which two objects charged by friction? So you need the rubbing to happen between these and the electrons to be lost by one and gained by the other. So the doorknob and you, the doorknob and carpet, you and the carpet, or the doorknob and the floor. So you have to ask yourself, where does the friction happen and the original electrons got transferred? You might notice it when you get zapped with the doorknob, but that's not a friction event, right? The friction happened when you scuffed your feet on the way to the doorknob going down the hall or something like that. In a car, I think the primary way is actually between the seat cushion and your pants or your shirt, or that's where a lot of the friction happens. That will charge you up when you're coming out of a car. Of course, if you're going into the car, it's the same thing. So the friction event here is actually letter C. It's between you and the carpet. And then you're carrying around those extra charges. All those electrons don't like each other, right? They repel. And so when they get near a conductor, like a doorknob, they're like, oh, great, now I can finally get away from all these other negative charges, right? Because don't forget, you've picked up billions and billions of electrons when you scuff your feet on the floor. So there's a lot of repelling going on. Okay, method number 2 is conduction, charge transfer by conduction. Now for this to happen, you already need to have a charged object. So you could have charged it up by friction, or it doesn't really matter, but in this case we're starting with a charged object. So we're reading this from top to bottom. So we have a negatively charged object near a neutral object. You bring the charged object in and put them in contact. That's what's supposed to be going on the second one. And now all of these negative charges, so I've only put one minus sign in here, but don't forget any sort of everyday amount of charge involves, trillions and trillions of electrons. And so they're all repelling each other, trying to get as far away from each other as possible. And so now by putting yourself in contact with a neutral object, those negative charges can now disperse and spread themselves out as far apart as they can. If they're two conductors, they will spread themselves almost instantaneously, evenly throughout the two structures. If they're insulators, then that process will be slower, but it will still happen. And then after the negative charges are spread around, charge still needs to be conserved. So if you look in this bottom picture down here, the total amount of negative charge here needs to add up to the total amount of negative charge in the original picture. So I had represented that by two negative signs, so I still need two negative signs down here. It's just now 50% of the charge is on the light blue and 50% is on the light orange over here. So that's charge by conduction. When you bring two objects in contact, the excess charge will spread around. So when you are zapped by the doorknob, where does that, wait, that's the same question. No, I went back instead of forward, sorry. After charging by conduction, the two objects are always. So what's going to happen if you bring these two objects into contact? Even if both objects have excesses of charge, they're going to make a common pool of charge, right? And if one was positive and one was negative, they'll cancel out to a certain extent. But whichever one there was more of will then spread out over both objects. So at the end of the day, both objects will be, letter B, the same charge. They'll either both be positive or both be negative, because when you leave them into contact, charges will transfer back and forth until they even out, right? And if they're not both neutral, then whatever the excess charge is will spread out on both objects. Okay, so when you neutralize something, that is a type of conduction, right? So you have a negatively charged object on the left and a positively charged object on the right. You bring them into contact. Now, when the electrons start transferring over, they will find a positive charge and they'll hang out and neutralize that atom. And that process will continue, right, until all of the positive charge that can be neutralized is. So if there's an equivalent amount of negative and positive charge in the beginning, that actually adds up to a net charge of 0, right? Negative charges on the left and positive charges on the right. And so charge is conserved by neutralizing both objects in this special case, because a -2 and a +2 is the same thing as a 0 plus a 0. Okay, so think about this example. What if you have two objects that are being brought into contact, and the object on the left has 3 times the amount of charge but negative, right? So 3 times as many electrons as the object on the right is missing electrons, right? So let's put numbers on here. Let's say there are 1,000 electrons that are missing on the object on the right, so it has excess charge of plus 1,000 protons, and on the left you have an excess of 3,000 electrons. What will happen after we bring these guys into contact? So look at the 4 choices, think about it, and commit to one of them. Okay, so if you just remember the rule that the charge needs to be the same sign on both, that will quickly get you to letter C, right? Let me talk you through how that will happen. So when you first bring them into contact, right, you can think there are 1,000 electrons that have like basically 2 reasons to go over here onto the orange. One is they're attracted by these 1,000 protons over here, and so that's reason number 1. And reason number 2 is there are 2,000 electrons repelling them over there, right? So these 1,000 will hop over right away, and then that will be neutral. But now there are still, say, 2,000 extra electrons over here hating on each other, pushing each other as far apart as possible. And so then they will go through that spread out procedure where those 2,000 will now get spread out. So you have basically 1,000 on the left and 1,000 on the right. Okay, and the third and final means of transferring charge is the most complicated one. This is called induction. It comes from the word induce, right? And in this one, like conduction, you're going to start with some charges in the area, but unlike conduction, you are never going to touch them. Notice that the positively charged object on the right never actually comes into contact with the neutral object. And therefore, since those charges are isolated, the 3 positive charges come in and then they leave at the end of the operation and they never actually get transferred. So with induction, the transfer doesn't happen between the charged object and the other object. Instead, what happens is in the other object, the neutral object in this case, just having the presence of the positive charges here is going to have an influence on all of the negative and positive charges within the neutral ones. For instance, some of the electrons in the neutral object will say, hey, look, there's a lot of positive charges over here on the right. I'm attracted to those positive charges. And so the right-hand surface of the neutral object will tend to accumulate more electrons than anywhere else in the neutral object. Now, for every electron that came over on the right-hand side, that means it uncovered a proton somewhere else, and now you have positive charges over there, because it still needs to be neutral, right? It's just going to have an induced charge separation with some positive on the right and some negative on the left. Now, if we ground it, and that literally means connecting it with a conductor like a wire or a person's finger or something like that to a really large reservoir of electrons, which is called a ground. So in electronics, any sort of large reservoir of charge that's convenient to the circuit is called the ground. It comes from the literal, earth beneath your feet being the largest reservoir of charge at all. So in the best of all possible worlds, you actually ground things into the literal ground beneath your feet. That's what the electricity in your house does, right? Now, suddenly you can actually exchange charges with the ground, right? So even though the neutral object itself doesn't really want to lose any electrons or gain any electrons, since it is near this positive charge is having a pulling effect on the electrons in the neutral, and that's going to pull some electrons right out of the ground, right? Those electrons from the ground are, in essence, trying to get close to these positive charges on the right-hand object. Even though they can't get there because they're not in contact, electrons will come up the grounding wire and hang out in the neutral object and turn it into a negatively charged object, right? The idea here is the ground is like the bank, right? It's got so much charge that it can spare you. You need a few million electrons, no problem, right? The ground is still relatively neutral. You can send some electrons down there, and the ground is not bothered either. There's so much place and surface area and so much charge there to absorb it. Just like you can go to the bank and make a deposit or withdrawal, and then the net worth of the bank doesn't really change that much. Right, so the key here is that the object on the left went from being neutral to being negative. That's the charge transfer, but it did not happen directly with the charged object in the area. Instead, it came from this sneaky connecting it to ground situation. Right, so here's a picture that shows the actual induced charge separation, right? This is the origin of all static cling problems, right? How can neutral objects get attracted to charged objects, right? And the answer is the neutral object has all these positive and negative charges in there. And if there is a charged object in the area, here you can see the induced charge separation. What happened was the negatively charged rod repelled some electrons in this ball, the metal sphere. And so those electrons went as far away as they could in the metal sphere, which made this top half negative. And of course, for every electron that left the bottom half, it left an extra proton down there. And so now you have a positively charged bottom half of the sphere. The sphere is still neutral, right? Equal number of positive and negative charges, but you've had an induced charge separation. And that's where the static cling comes from, is because these positive charges are closer to the negative rod and than these negative charges are. And so positive charges are attracted to the rod, and the negative charges are repelled by the rod. But unlike in the first picture where they're all mixed together, the attracting and the repelling just cancels out, and you don't have any sort of net effect. Here, under the induced charge separation, you have an attractive force because the attraction between these positive charges and the negative rod is stronger than the repelling between these negative charges and that, for the simple reason that the positive charges are physically closer, right? We'll talk about that on a different lesson, but electrical forces are just like gravity. They depend on distance. In fact, exactly like gravity, they're 1 over r squared. Now, if you ground the object, the ball, while it has this induced charge separation, remember these electrons are up here because they're trying to flee. They're trying to get away from the negatively charged rod. So if you give them a pathway to the ground, they can flee all the way, and they will leave the sphere entirely, go to the ground, and then if you cut this wire or remove the contact, you now have a positively charged sphere, right? And so this sphere has been charged by induction, right? All induction goes through these steps. Induced charge separation, which is not enough to charge it, but enough for static cling, then it's this grounding that allows you to actually make the object charged, and then you have the charge. So if you're following that, what's the rule here, right? If you've charged an object through induction, you've gone through all those steps, induce the charge separation by an external charge, ground it, allow the charges to move around. What are you left with in the end? Will the object that has been charged be opposite or the same in sign as the nearby object? Right? You can cheat and go back up here and see what happened, right? The negatively charged rod made the sphere positive. So the answer is it's going to be opposite. All right, so let's go through this object. I've got a neutral object on the left. This is a grounding wire that you see going to the left off the page. I'm going to have this positive charge nearby. I'm going to bring this positive charge nearby, but I'm not going to touch it. So what's going to happen inside of the neutral object? And then I'm going to remove the grounding wire to trap it. So will they both neutralize? Will they both be positive? Will the one on the left be negative and the one on the right be positive, or negative and neutral? So the first thing to do is to realize nothing's going to happen with the object on the right. It's not being, there's no charge transfer happening to it. So if it's +2 in the beginning, it's got to be +2 in the end. So you can eliminate A and D. So now you're down to C and B. So you can use the rule, which is that they're going to be oppositely charged because this is charging by induction, which will get you to B. But better is to think it through, right? What's going to happen to the neutral charges is negative charges are pulled to the right to get close to those positive charges. So that means some electrons are going to come up this grounding wire from ground and hang out in the neutral charge to try to get close to those positive charges. So the neutral is going to accumulate some negative charges, which you can then trap in there if you cut this wire or remove this wire. So letter B is the correct answer. Okay. Yeah, okay, let's just do a couple more. Static cling of your socks. So you take your socks out of the dryer and then they just they stick to your shirt, like even the shirt you're wearing. What happened there? Did those socks get charged by friction, by conduction, or by induction? Well, when you put the wet socks in there, everything was neutral, right? The dryer was neutral and the socks were neutral. So it's not going to be conduction. And probably nothing got grounded, so it's not going to be induction. What does happen, though, in the dryer is things get tossed and turned, and they scrape against each other, and the socks either accumulated or lost some electrical charges. I don't really know because the effect would be the same in either case. And so then you go to pull those socks out of the dryer, and now they are the charged object. And your shirt, say, is neutral, of course, but because of this induced charge separation, right? In this analogy, this would be the rod would be your socks that came out of the dryer that have been charged by friction. And why do they stick to your neutral shirt? It's because of this induced charge separation. Right? When your hair stands up, when you're standing near a high voltage source, why is your hair standing up? So you're probably not actually charged at this point, but each hair on your head is now carrying either an extra electron, or 2 or 1,000 or million, or every hair on your head is short 1,000 or million electrons and therefore positively charged. Since they're all negatively charged or all positively charged, they are going to repel, and that's why they're standing up on their head. So the reason why that's happening near a high voltage source is the high voltage source is inducing charge separation in your body, right? So you may still overall be neutral, but of course, if your feet are on the ground, then you are grounded, and so you will become charged by induction, letter C. All right, so when you discharge, when you touch the doorknob, right, you're the charged object, and you're touching the doorknob, those charges flee your hand. So that's charged by conduction because you're touching it. Even if you are very close to it, right, and you get zapped, maybe you weren't quite touching the doorknob, but why did you get zapped is because you got your fingers so close that the air basically wasn't acting like a good insulator anymore, and those charges basically made a little conducting pathway through the air between your fingertips and the doorknob, and they all channeled through there, right? So in essence, it was as if you were in contact via the air. All right, this is a demo that will have you try at home. Maybe you've already done it by now, but if you have a charged object and you are running a faucet with a very weak stream of water, you can show that stream of water getting pulled towards the charged object. Doesn't matter if the charged object is negative or positive. And that is an example of static cling again, right? So what's going on is the stream of water is neutral, like the sphere up here, But if you have a charged object in the area, you'll induce charge separation and you'll create a net attraction, right? Static cling is always attractive. Right, so here's a picture showing you that charge separation. This pink box here is neutral overall, but in the presence of a positive charge, in this case on the left, some negative charges will be hanging out on the left-hand side. Positive charges will be as far away as they can, even though the overall effect is neutral. Since you have opposites closer, you've got the opposites will attract, outweighing the same charges will repel, get an overall attraction. Right, so it's never static repulsion, it's always static cling. So if you're inducing a charge separation, the object that is inducing it is always going to force the opposite charge to be closer, and therefore you're going to have an attractive effect under induced charge separation. Okay, thanks for watching.